The last topic that we'll discuss from Chapter 1 of the Methods text is errors. The absolute error is defined as the difference between the true value of a variable and its approximate value, x tilde. The absolute error is positive when the approximate value is less than the real value, and the absolute error is negative when the approximate value is greater than the real value. The absolute error can arise due to modeling error, truncation error, or rounding error. Modeling error is an error in the method used to estimate the value of x tilde. Truncation error occurs when we truncate terms in an infinite series, or when we stop an iterative method that estimates x tilde. We should note that the absolute error has the same dimension and scale as the value x and the approximate value x tilde. Relative error is a normalized value. It's the absolute error divided by the true value. The relative error is normalized to the value of x, and it's therefore always dimensionless. We use the relative error to compare two errors that might be on different scales or be represented in different dimensions. We should note that when the true value is 0 or very close to 0, the relative error can be quite large or even undefined. When we know that the absolute error has a magnitude less than or equal to some value, or when the relative error is less than or equal to some value, then we can call those values, alpha or beta here, the upper bounds on the absolute and relative errors respectively. To propagate these upper bounds, or these error bounds, for sums or differences of two values, the upper bound on the absolute error of the sum is always less than or equal to the sum of the upper bounds on the individual errors. But that same formula cannot be used when two variables are combined as either products or ratios. You should use the formulas shown here for upper bounds on relative errors of products and ratios. These equations are also given on page 17 of the methods text. Here's what we reviewed in Chapter 1 of the methods text. We reminded you that you know how to use the I-factor method for solving linear first-order ODEs, and you know how to use the method of undetermined coefficients for solving second-order linear ODEs with constant coefficients. In the next chapter, we'll talk about some tools in MATLAB that you can also use to solve ODEs. We talked about the determinants of a square matrix and some of their properties, and we showed how this can be used in Cramer's rule to solve systems of linear algebraic equations. We also showed that the determinant is an important quantity that's used when solving the matrix eigenvalue problem. Finally, we introduced error bounds and some information about error bound propagation when two uncertain values are combined in either sums and differences or products and ratios. There are some other topics in Chapter 1 of the methods that you should also review, but that we didn't cover in these lecture slides. Topics like the matrix inverse, similarity transforms, and matrix diagonalization are also very important, and we'll revisit these later in the semester, so there's no need to cover them right now. The last topic that's covered in the first chapter of the methods text is iterative methods and their convergence. Convergence is going to be a very important topic for us as we go on. You should review the content in Chapter 1 of the methods text on iterative methods and their convergence, and we may discuss this in class.